All right, guys. So we talked about bacteriophages, and that was terrifying. So let's talk now about animal viruses. I feel like those matter more to us because we're animals. So there's a lot of overlap between bacteriophages and animal viruses, which thank God, because I want them to have to learn as little as possible. So they kind of start off with like infection the same way. There's the attachment, the spikes, the membranes, whatever, um, interact with receptors onto the host cell. There's the penetration, and for animal viruses, usually there's whole entry of the virus into the animal cell. Um, so this occurs via two ways. The envelope fuses with the plasma membrane, and the nucleocapsid, which is, I think, just a fancy term for the entire virus, enters into the cell. Or it can occur when the virus is taken into the cell via a vesicle. So, like, it's in something else, and something else goes inside the cell. Um, which then fuses with the envelope, releasing the capsid into the cytoplasm. So that's that one. Anyway, I hope there's not a lot of questions on this. Then there's the uncoating, which sounds like pretty the sexiest part of all this. So the viral nucleic acid escapes the capsid, which makes sense because we said that basically the whole unit gets in. The bacteriophages just like squirted the RNA in there. So there's the synthesis, so they make all the raw components. Yeah, so and this is also when things could be latent. There's the maturation or the assembly portion, so they're making everything together. And then there's the release of viral capsid, and those are mature virions. Yeah, so okay, so we mentioned naked and enveloped viruses earlier, right? So the naked viruses just lyse everything, 50, 200 all coming out or something. And then the enveloped viruses cannot be a budding because they want that cell membrane to cover it. So they just kind of like pinch off and they steal some when they go off. Anyways, that's budding. So like the bacteriophages and their prophage, the little section of the DNA that would be into the host cell's DNA to get free replication. For animal viruses, they call it provirus. The virus becomes a part of cell DNA, causing latent infections, or it can cause latent infections. During a latent infection, there's no active viral replication. Both DNA and RNA can make latent infections. So, like, what's cool about latent infections? It's free replication. The host cell does all the work, and you just keep getting all this cool replication. So that's neat. It also lets it do an acute infection later, and also the immune response can't go inside its own cells. It lets them hide out really, really well inside cells, so they can stay for a long time. So how do you cultivate viruses and do lab work shit for it, right? Like this is a microbiome class. If it wasn't still kind of pandemic season, it's a tail end of it though. Then I'd be doing labs, but instead I just watch other people do labs via videos that on YouTube, and just think about what I would do if I did labs. So anyway, if you're going to actually fuck with labs fuck with viruses in a lab setting, you can't use an agar play or anything like that. These viruses need cells to grow into, right? So historically, we've used live animals, like monkeys and shit. But now it's a lot more common to either do embryos, like little chicken embryos. You can do shit that way, or you could do cell tissue cultures and get some tissue cells and grow them in a culture, and you can check for evidence of viruses that way, or look at the prophages that could be in there, or the proviruses that could be in there, or just all the tons more viruses that lysed out of a cell and are floating around. Also, these viruses can make cells look really fucked up. and weird, like in malaria. And that's called cytopathic effect. That is a visible effect on the viral infection on the cultured cells. It could be cell swelling or like fusing together, cytopathic effect. So like, how do you even control viruses? Like, what do we do here for like control? You can treat the infections that we shorten the amount of time it could be infectious, and that's important. Less infections, we shorten the infection time. You could prevent the disease in the host via vaccination, or you could interrupt the transmission of it so that people don't get infected in the first place. So let's say like you got a virus, right? Like how do you fix it though? Like what's the therapy for viruses? Obviously, you can't take antibiotics, or antibiotics are not useful in the sense that viruses are not fucking bacteria. So that's not going to help. I could imagine, like, because everything is so nuanced, right? That, like, maybe if you had like a virus that lived inside a bacteria, that was what was inside of you, and that the bacteria, like, I don't know, like you could maybe kill the bacterial cells with an antibiotic, and that would, by proxy, take care of the virus, maybe. But anyway, just like you can't, antibiotics are for bacteria. Antiviral medications are for viruses. Um, bacteria are prokaryotes. Animal viruses are eukaryotes. And so that changes like the medications that you would need. Antiviral drugs often have pretty like severe side effects. It's hard to kill. I mean, you can't kill what's not alive, but it's hard to kill a virus that's inside your living cells without also killing your living cells. So that's a problem. The best solution we got so far regarding antiviral therapies is that the medications prevent the replication of the virus. They're less effective compared to antibiotics. But yeah, so anyway, what does your body do, right, for viruses? It sounds like it'd be a shit show, and we're just all SOL anytime you come across viruses. Kinda. Like, yeah, kind of. So what I wrote down was running interference, kind of like running interference. So when your infected cell that has a virus in it is dying because the virus is fucking shit up, it releases a protein that binds to healthy cells and lets that healthy cell know that like shit's going down, and it makes it hard for when the virus comes to infect that healthy cell for that virus to be able to replicate. Um, as a non-specific host reaction, it works for like a lot of different viruses. It's not super unique. Um, and I think, yeah, and the interferon is the name of what the dying cell sends out. The healthy cell that makes the antiviral protein, that probably has a name, that protein. I don't know what it is, though. It's not interferon, according to my notes. And then there's like a lot of talk about vaccines in this as well, regarding attenuated and non-attenuated vaccines, and the goal for shit. I don't want to talk about vaccines all day. I mean, I love vaccines. Vaccines are great. I got vaccines like on deck. Um, but there's the attenuated virus. That's a live virus. And then there's the inactivated virus, which is also, I mean, they're not alive, but anyway, for the virus that's a live virus, they make it so that way it's extremely slow and difficult for it to replicate. So it gives your body just ample time to come up with a successful immune response to it because it's not going anywhere fast. Inactivated viruses are considered like killed, and so they're not going to be able to replicate at all, and it's a lot safer for like people who are like immunocompromised and shit like that. And then there's subunit vaccines, which I forgot about or didn't learn about in my infection control class in RDA school, and that's when one component of the virus, usually a protein, stimulates the host response. These are not as effective, I believe, as these other ones, um, but they can be made with genetic engineering. Hepatitis B apparently is a subunit vaccine, but that makes sense because you kind of got to like get multiple hepatitis B vaccines. You get titer draws and shit. Anyway, So there's that. Animal viruses.